I really quickly want to give you some answers or feedback on this to me if you have tried it already. In grade 12, you learned to model exponential growth with, I don't know what's going on here now. There we go. You learned to model exponential growth with a function that looks something like this, right? A times b to the power of x. You may use different variables. You may say y equals y0, like the initial value, times r to the x, or r to the t, or somebody might say like population is initial population times r to the t. Whatever variables you use, you usually look at it as something times some kind of exponential expression. You even look at some that involve the letter e, the number e. E is a number, and that's part of where we're going here. If you've already written something for this, writing a model function, if you have something starting at 250,000, maybe you use p for population, 250,000 times some rate to the power of t here. If you have, this is your 250,000, this is your population at the beginning, that is 100% of the population. If it's growing at 4%, what percent do you have left over at the end? At the end of every year, you have 104% of what you had the previous year. Every year, you multiply by 104%. If somebody says, here's a bag of chips, and here's your original bag of chips, and it says, often they make it visual like this, now 25% more, right? What percent is that bag of the original bag? It's 25% more, but the entire bag is 125% of the original bag. I tell you this, maybe you don't see why I'm telling you this, but if you're modeling this, you need to put in 1.04, 104%, not 0.04 if you're modeling it like you do in grade 12. It's got to be you need the original amount, right? If you multiply something by 1.04, you get, the 1 gives you the original amount, right? 100% plus 4%. This gives you the original people, this gives you the new people. So that's your function. If you're graphing that function, see if I have my calculator still out here. Come on. Not that. If you graph it on your calculator here, 250,000. If you guys could stop talking, that would be very nice. I know you're probably talking about this, but you'll have some time after to look and discuss things. That's that function. If you're setting up a window for this, maybe you need to, maybe you need to change it a few times, but I'm thinking I'm going to go up to 20 years down the road, maybe make the scale once every year. Probably the population is going to be 400,000 or 500,000 or something like that, so I'll put 400,000. I am actually going to start at negative 100,000, not because you can have negative populations, but because then when it shows the graph, there'll be some space underneath it so that my numbers won't cover it up. I'm going to make my scale 100,000. It doesn't matter what you make the window, it's still the same graph. So there's my function. I actually should have gone up higher than 400,000 because it goes off the scale before 20 years. Go back one more time, change it. We'll change this to a 5. 4% is not a very big growth rate. You maybe should make some mental notes of this, not for population growth, but for investing money. 4%, it looks pretty straight, right? It almost looks like it's just simple interest, like it's just going up at a straight line. If that was a higher percentage, there'd be more of a curve to it in the short term, right? To get to see that it really curves up and ramps up, you've got to go out to quite a few years here. And 4% is even higher than an interest rate you get nowadays from a bank. But if you want to find some answers here, I was thinking, so you're drawing it here. If you're copying a graph down ever, put down some dimensions here, 500,000. And it looks, what's the y-intercept, by the way, for that graph? Without actually finding it on the calculator. Yeah, starting value, right? That's the starting value. It's got to start at 250,000 and go up like that. If you want to use the calculator to determine the population after 12 years, you're just using this calculate feature here, value. It allows you to put in a number and it'll give you the population. 400,000, 258. Don't put the decimals. No fractions of people, right? 400,000, 258. Keep in mind that when you model something mathematically, like if somebody's doing this modeling for a city or for some planning for something, don't wait 12 years and then expect exactly this many people. In reality, it's not going to be exactly that. This is a model. That's our best prediction right now, but it's a model. And in real life, in 12 years, it's going to be something different probably, but that's our best guess. If you want to confirm this analytically, as in algebraically, without using the calculator, how could you get it directly from this? What can you do? What do you think?
1.04 to the power of 4 times.
Yeah, absolutely. You put the number in, right? Substitute it in. And it should give you the same thing. Part of this course, even if you look on the front cover of the textbook, it says Calculus, Graphical, Numerical, Algebraic. Part of what the goal of this course is to have you realize you can look at things a couple different ways. You can look at it algebraically, you can look at it with a graph, and you learn and you understand a lot more looking at it a few different ways. If you can come up with an answer one way and a completely different way, that's pretty powerful in terms of having you realize that you've done it the right way, right? Oh, stupid updates. Determine when it'll reach 300,000. That requires you to work backwards. This, just so maybe you can keep it in your mind here, understand, this asked you to pick an x value and then look at the y value, right? It said, go to 12 and then look over here at what the y value is. So this was, given an x, find a y value. This is the other way around, right? This is given a y value, find an x value. So we're going to do two ways, on the calculator and algebraically. I asked you to do it algebraically first. Get rid of our bag of chips here. If you're going to find this algebraically, what could you do? How do you do this? You have our function already.
300,000 equals 250,000.
Absolutely, yeah. Put that number in there and then solve for t or x or whatever you're using, right? Put this in here, and then you need some logarithms. So some of you might be taking Math 12 concurrently. You're working on logarithms right now, hopefully in your class. If you want to start to solve for this, you got to start to isolate and get rid of other things. So you could divide by 250,000 first. I'm just going to put 30 over 25, not 300,000 over 250,000, because when you're dividing, you don't need all those zeros. The key, even if you haven't done solving with logarithms in your Math 12 class yet, to isolate that if it's in the exponent, you need to take the logarithm of both sides. So logarithm of that equals logarithm of this. That's how you start isolating for that t. Start isolating it that way. And then something that most Math 12 students are good at is they remember this rule, the power rule for logarithms. They remember that, and you have to watch carefully here, okay? They remember that this, if for that expression, that t can go in front here. Log of 1.04 to the power of t is the same as if you put that t in front, okay? You want to see a replay of that? Here's a replay of that. Ready? It's not slow motion replay. Make sure you're okay with that idea that log of 1.4 to the t, put this in front, and then you could just solve for it, because it's just t times this number equals this number. Both of those are just numbers. You can solve for them. So this is going to be log of whatever 30 over 25 is divided by log of 1.04. Anybody put that in and can tell me what you get approximately? 4 point something?
4.65.
4.65. Good. Okay? How would the original function be different if it was, I didn't want to ask you to go through and do it all over again with that. How would it be different if it's declining at 4%? Go back to our bag of chips here. Well, they're not going to advertise this, but now 4% less. Well, I guess they could say 4% less fat or something, but 4% less. If you had the original size, but now you're not adding on, you are taking off, what percent are you going to have left every year? 96, right? So your function's going to look like 300,000, no, 250,000 times 0.96, right? It's whatever percentage is left at the end. You start with 100%, you lose 4% every year. It's that. You're always multiplying by, every year you're multiplying by 96%. We should probably be okay with function notation too. Sometimes it's going to say y equals for a function. Sometimes it's going to use function notation. If you're using p for population here, you could say p of t, population, as a function of time. So just make sure you're okay with either one that you see. Are we okay with that?